Okay, to further illustrate Bernoulli's principle, I'd like to balance a ping pong ball on a column of air. So this might seem kind of astonishing. I have such nerves of steel that I could do this. But then we realized that maybe I don't have to be very talented because my margin for error is huge here. I'm able to get the ping pong ball to extend out this far in either direction, and it still doesn't fall. And then if I give it a little tap, it likes it in there. There's a restoring force that actually keeps it in there. And if I put another ball in there, I can get them both, unless they collide with each other, I can get them both to, wow, setting a record. I've done this before with 3, but usually can't do it for that long. So eventually, though, you get to the point where they can't handle it anymore. So we might wonder then, well, what causes that? Well, I can show you here with some streamlines of air. And the relevant part of Bernoulli's equation that works for airflow, which is P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Okay, and so if we've got a ping pong ball and here's a bunch of air coming out, what's going to happen is that the streamlines of air nearby to the ping pong ball are going to be traveling faster than the air that's farther out. So if we call this V1 in here and this V2 out there, then if, like in the last example, V1 is greater than V2, then in this equation that means that P1 has to be less than P2. Right? Because a smaller value for P1 plus a bigger value, so this is internal energy per unit volume, this is kinetic energy per unit volume, has to equal a bigger value for P2 plus a smaller value for the 1/2 rho V2 squared term. Okay? And so that shows us then that the pressure out here is greater and the pressure in there near the ping pong ball is less. So if we think of this as being larger pressure, and then in here we have this as being lower pressure, then we can see that as the ping pong ball starts to move in either direction, you've got a wall of higher pressure air that's tending to force it back in. So that even if you tip this thing at an angle, you still have that higher pressure air supporting a component of that weight of the ball. And so these kinds of applications then can be used in sports. If you've got a curveball, basically what's happening is that there are little irregularities on the baseball itself that are, if that baseball happens to be rotating, that are going to either cause that baseball to rise or sink, depending on where the air is moving the fastest. Okay? And so if the baseball, say, is rotating this way, and the airflow is that way, then a higher velocity is going to happen over the upper surface of the ball, and a lower velocity is going to happen over the lower surface of the ball. Why? Because the rotation of the ball carries air along with it. And so that's why the pitchers can mess up the ball a little bit by scruffing it up with, say, a fingernail file or something. And so that's what they do to cheat. They mess with the ball to allow for the ball as it rotates to carry more air along with it. So if the air is being carried this way, but the airflow is that way, then that gives you a lower velocity, but that gives you a higher pressure. Okay. And so a lower pressure then would be up here, so this would cause the ball to want to rise up. Okay. Now, that may not be the best strategy for a pitcher, because if the ball rises up, then that just reduces the amount of parabolic path of the ball and allows the hitter to just tee off on that thing because it's not curving much. But if you reverse the direction and made omega go this way, then this would become the high pressure, and that would force the ball down. This would become the low pressure or higher velocity if the omega were going the other way. And so that would be a sinker ball. And so you've got all these different kinds of airflow effects that are associated with Bernoulli's equation. Also, the surface of a wing, I'm sorry, the surface of a house, I should say, can cause the roof to take off. Because, let's say, for example, in the Florida area, they built a whole bunch of homes there, and they use substandard material to anchor down their roofs. And so, with a higher velocity of airflow here, we call this V1, and then very little airflow here through the inside part of the roof, because the roof is blocking the high velocity winds. Then this gives us higher velocity, but that gives us lower pressure. Because we have high velocity. Okay, so here we've got lower velocity, and that means high pressure. And so that high pressure then will tend to push up on the surface of the roof, and so that roof can just take right off. If it's not held down properly, the roof is gone. Okay, and so that's happened in a whole neighborhood where new homes had been produced all at the same time by the same construction company that had used substandard materials to anchor their roofs. And here's another example, this kind of a thing, is the fear that we all have in an intense windstorm that our umbrella is going to turn inside out. And so as we're watching this roof get torn off, and we're laughing, and then here what happens is you're holding onto your umbrella, you get that strong lift force, and all of a sudden the umbrella turns inside out. And unless you've got a really expensive umbrella, that's going to wreck it. Okay? And so it serves you right for laughing at that roof that just got torn off. Your umbrella was just destroyed. Okay? And so these are all examples then of Bernoulli's equation as it applies to airflow. But why? Okay, well, before I get to why, let me just do one more what. Can I borrow that piece of paper just for 1 second? I'll give it back. Okay, so here I'd like to set up just a quick little demo. Now you might think that faster velocity air is going to have associated with it more pressure, because if the air is moving through faster, then shouldn't that lift something up? Well, here, let's check it out. You can see this. Now I'm going to blow air through here, okay? So I'm blowing it through the bottom of this thing. So if that idea is right, that faster velocity air will create a pressure this way, then this whole thing will lift up. But if Bernoulli's equation is right, then faster velocity air should be lower pressure air, and it should smash down like this. Okay, because I'm blowing the air through here, not over the outside of it. So let's try that. Look at that, just flattens right out. every single time, flattens right out. So faster velocity means lower pressure. Then the higher pressure air that isn't moving as fast from the outside can smash it flat. Okay, and so why? We see that that is the case, but why? Well, this explains kind of what's going on with a wing, too, if we're trying to explain why the airplane would fly. And so think of it this way. You can think of pressure as just being related to the motion of the molecules in the gas making collisions with the wing surface. But if the air itself is moving too, then that means there's less energy to put into the internal motion. And the internal motion is what makes collisions with the wing. So if I'm going slower like this, I'm making more collisions with the wing surface per second. But if I start moving faster, then I'm making less collisions and therefore less pressure. So what's happening then is that the energy is being divvied up between the motion of the flow of all of the air together, but then there's also that internal energy if the air weren't moving at all. And so these are partitioned out by these two different terms, so that if you have more of this kind of motion, you have less of that kind of motion. And similarly over here, if you have less of this kind of motion of the whole fluid flow, then you have more pressure, which is more of the internal energy, which creates collisions that generates the pressure. And so that is why an airplane flies. Next, what I'd like to do is write out Bernoulli's equation in all of its glory with the rho g y terms, and we'll look at a problem that involves liquid fluid flow. So here we have P1 plus 1/2 rho V1 squared plus rho G Y1 equals P2 plus 1/2 rho V2 squared plus rho G Y2. And so let's try this now for a container of water. Okay, and let's say that the container of water is filled to a height of 10 meters. Okay, so it's a big water tank, big cylindrical shaped water tank. And so we'll call this point 1 in the median. And let's say that there's a house that's on fire down here. And so we go, I know, what I'll do is I'll blow a hole in the water tank right here, and that'll put out the fire. Okay, so we'll make a little hole here at a point 2 in the median that is 1 meter above the ground. So this is 10 meters, and here this is 1 meter, where point 2 is located. And so let's find the velocity of fluid flow out the hole. V2 equals question mark. Okay, so how do we do this? Well, first of all, at point 1 we have P1, but that's just P atmosphere. And then down here at point 2 we just have P2, but that's also P atmosphere. Okay, so that's the external air pressure pushing in on these fluid surfaces. Now here P2 may not quite be P atmosphere, because of the fact that there is a velocity of fluid flow that then will carry along some air molecules. You can feel a little bit of air flowing near rapidly moving water. And so the air may get moving a little because of the motion of the fluid. But I'll still neglect that effect here and say that P2 is about the same as P1. And it's also going to be a little different because we're at a slightly different elevation. Here, we're 9 meters higher. Now that's not a big deal. You're not going to be popping your ears because of a 9-meter elevation difference. And so because of that, I can say that P1 is approximately equal to P2 for this problem. And so that means I can cancel them out of my equation completely. Now notice that those were the terms that were the most significant terms for the airplane. So for the liquid fluid flow, the atmospheric pressure terms are usually about the same and can be canceled out of a problem like this. And so what we're left with then, I could call this point here y2 equals, I could call it 1, or I could call it 0. If I call it 0, then my y1 height is going to be 9 meters, because this was 10 meters, the water level above the surface of the ground, and point 2 was 1 meter above the surface of the ground. So the difference in the height is all we really need here for the 9 meters. Remember that our goal was to find V2, the velocity of fluid flow out that hole. Now, how little is the hole? Well, it turns out it doesn't matter in terms of the velocity. In terms of the flow rate, it does matter, but not in terms of the velocity itself. Okay? And so we can rewrite Bernoulli's equation now, but with V1 approximately equal to 0. Now, is V1 truly equal to 0? Well, no. But if this is like, for example, the surface of a bathtub, and that's dropping very slowly relative to the velocity that the water is going out the drain, which would be the same kind of a problem here, at least in basic outline, then V1 is small. Say V1 is 0.1 meters per second, and V2 is 10 meters per second. Then 10 squared is 100, and 0.1 is 0.01 when you square it. 0.1 squared is 0.01. So if this were 0.1 and this were 10, okay, then this would be 100, this would be 1/100th, and so there would be a difference of 10,000 between the two terms. So because it goes like the velocity squared, small values of the velocity allow us to throw that term out too. And then just by making life easy for ourselves and making the bottom point our reference position for y equals 0, we can get rid of this term. And so now we have something that looks an awful lot like a conservation of energy equation. We can say that 1/2 rho V2 squared equals rho g y1. Or V2 is equal to the square root. The rho's are going to cancel, so that means the velocity doesn't even depend on the density of the fluid. That's kind of interesting. Equal to 2gy. Okay, and so that's something that we got as a result before for our energy equation. If you had, say, a pendulum that was swinging down, and it had 0 velocity up here, and it swings down to some lower position, the velocity at that point is the square root of 2g times the height. Or if you just took a mass and you dropped it through this vertical height, it has that same velocity as the velocity of fluid flow out the hull. So although these problems aren't the same, they do have some mathematical similarities to them. And so given that that's the case, let's go ahead and solve for V2 and then see what we can do with that. So V2 then, the square root, 2 times 10 meters per second squared. Not being that accurate here, but we don't really need to be. Times 9 meters. Take the square root, and we get 13.4 meters per second. Now, interesting, and this would be about 25 miles an hour. So what's interesting here then is that the fluid, as it flows out at this pretty high speed, would have the same trajectory as a mass that's projected at that horizontal velocity. So you could figure out if that's the right height to make the hole so that the water flows down and puts out the fire of this house down here in this complex. You could actually just do a kinematics problem on this with the parabolic motion of the fluid being the same as it would be for an object that's projected horizontally, that is just a single mass. Okay, and so we might then wonder, well, does the size of the hole play any role in what the velocity would be? The answer is no. The size of the hole plays no part. Unless there's enough water flowing out this hole so that this V1 term is significant. Okay, and so in other words, if you knocked out the whole side of this water tower, then V1 would be comparable to V2. And then you could not justify throwing out this 1/2 rho V1 squared term. So this is true then unless V1 becomes comparable to V2. Or more specifically, V1 squared becomes more comparable to V2 squared. But as long as V1 and V2 differ by, say, factors of 100, then 100 squared is 10,000. They're not comparable in that case. And so the size of the hole doesn't affect the velocity, which might be a little surprising to some of us, which might think, well, if you make a bigger hole, the velocity is going to be bigger. But no, the velocity is the same. What changes, though, is the flow rate. And so that's what I want to talk about next. Flow rate we can get by looking at, say, a tapered pipe, and then we make the condition that the flow in equals the flow out. Okay, now that must be true if we have an incompressible fluid, because if the fluid can't be stretched apart or squeezed tighter together, then the mass of fluid flowing in any given length of time has to equal the mass of fluid flowing out in that same amount of time. That's just conservation of water in this case. We're just saying that water wouldn't be created or destroyed. If you had more water coming out than came in any given length of time, it means that you'd be creating water in there, but you're not doing it, clearly. And so if this velocity then is V1 coming in and this velocity is V2 going out, I think that intuitively you could guess here that V1 is going to be greater than V2, because it's got to hustle to get the same amount of water flow through here. But then here, because there's a bigger area, then that, in other words, if you had this amount of water moving through there, then that might correspond to this amount of water moving out. This might be the same mass as that volume of water going in as going out. But if this water moves that far, this water moves that far, then V1 is greater than V2. Okay, so we call this X1, call this X2. We could say that mass in equals mass out. So the mass in then, through here, is going to be equal to, well, that's density times volume. So that's the density of water, in this case, if this is a water tube, times the volume. That's going to be X1 times A1, okay, where this area here is A1. Whereas this area here would be A2. And the volume that's associated with that would be X2A2. So this would be density times X2A2. So that's mass in divided here equals mass out here. But mass in per unit time is our flow rate. So we could write this as X1 over T, and this is X2 over T. And so the flow rate in, say in gallons per second, or in cubic centimeters per second, or however else you want to measure it, is going to just be equal to, well, X1 divided by T, that's just the velocity, V1. So we can say that rho V1A1 equals rho V2A2. And so this then would be our flow rate in mass. And this is sometimes called our equation of continuity. Okay? But because the density terms are the same on both sides of the equation, they can be canceled out. Okay? And we're assuming here that something like water is an incompressible fluid. This volume here we're saying is the same as that volume there in any given length of time. Okay? And so the mass in per unit time divided by the mass out per unit time gives rise to a mass flow rate that's equal to density times velocity times area. Okay? And so this would be in units of kilograms per second. So we might ask then, in this problem over here, if the radius of the hole is equal to 1 centimeter, let's find the mass flow rate. Out the hole. And so the mass flow rate then is going to be density times velocity times area. And so we already know what the velocity is. We have to figure out the area. The density is the density of water, 10 to the 3 kilograms per meter cubed, times the velocity, 13.4 meters per second, times the area. So the area is going to be pi times 0.01 squared, because the radius is equal to 10 to the minus 2 meters. Okay? And so what this is going to be then is 1.34 times 10 to the 4, because this is 1.34 times 10 to the 3, and then pi is 3.14 times 0.1 squared, that's 0.0001, or 1/10,000th, 10 to the minus 4. So the 10 to the 4 and the 10 to the minus 4 cancel, and that gives us our mass flow rate is going to be equal to 1.34 times 3.14 kilograms per second. Or 4.2 kilograms per second. Okay, and so that would be something like a couple pounds of water per second. And so that's a relatively large mass flow rate. What about our volume flow rate? Well, our volume flow rate is in units of meter cubed per second. This could also be in gallons per second, you know, if we wanted to do it that way. But here, we'll do it in our metric system of units. We can get that from just taking density times velocity times area equals density times velocity times area at some other point, and then canceling out the densities. Okay, so if the densities are gone, then we have units then of meter cubed per second. Okay, so that's what we want. And so for this problem, then that would be 13.4 times pi times 10 to the minus 4. So that was our 0.01 squared. So that's our velocity, 13.4 times pi r squared. This was 10 to the minus 2 squared is 10 to the minus 4. That gives us pi times 13.4. And so that's 4.2 times 10 to the minus 3 cubic meters per second. Okay, so it doesn't seem like quite as much when you talk about volume flow rate. When you talk about mass flow rate, basically you have to include the fact that the density term is an extra factor of 10 to the 3. Okay, and so if by not including that density factor of 10 to the 3, then you get it in cubic meters per second, whereas here you get something that seems a little more substantial in kilograms per second. And so that's how we could calculate the rate at which water is flowing out that hole. And so that is, of course, something that is interesting. Now, what if we had a siphon? A siphon is kind of an interesting problem because in a siphon, you might, for example, have a swimming pool and the drain is clogged or whatever, or a bathtub, you're trying to get water out of your bathtub and you can't get it out the drain, and so you siphon it out. Okay? And so the basic idea then with the siphon, if this is the fluid level, then there's a certain distance y1 from where the water is coming out here in the siphon, and that has to be lower down than the level of the water surface where you're drawing the water out from. Okay? And so we could call this then point 1 in our medium, and this point 2 in our medium. And if we do that, then what we did before for this problem with the hole in the water tank is exactly the same. Okay, and so let's say that y1 here is equal to 9 meters. Then by taking this difference, what we then have to do to get the siphon primed, so we have to get enough water in the tube to get to here. Okay, and so if we can draw enough water out of the pool to get it to there, or sometimes what you do is you just turn on a hose, and then you fill the whole hose up with water, and then you unhook the hose from one side, and then make sure that that's lower down than the level at the top level of the swimming pool, for example, that you're trying to siphon water out of. Then you get it a little past that point, and then the extra weight of the water on this side will draw the water up and out. Okay? And so the water will flow out with a velocity here. Guess what it's equal to? Same thing, 13.4 meters per second if this difference in height is 9 meters. So in other words, a problem like this water tank problem is indistinguishable in terms of Bernoulli's equation from the setup for our siphon problem. And so you can also do this with gasoline. And so notice that the densities cancel, and so you could draw water out of a gas tank using this same kind of a principle. And so what will start to happen after a while is the level of the fluid will drop, and that'll mean that the y will drop. So y is not constant in this problem, but y is a variable. And if we wanted to try to figure out how long it would take to completely drain the water tank, that's a tougher problem, because here we're just looking at the velocity at this moment when the height is this value. And that's a little different than integrating all of those little velocities out to get some average flow rate over the entire time that it would take to drain that whole water tank or to drain out this gas tank. Okay? And so that's another problem that's equivalent to the one that we just looked at. And next, what I wanted to do, oh, and by the way, for this equation of continuity, if the velocity is faster out here at this end, then a nozzle on a hose is going to work nicely because maybe the water isn't going to flow out fast enough, but then you put the nozzle on, then the water shoots out really fast because it's a smaller area and therefore a bigger velocity. So then you can catch those other plants that you couldn't reach because your hose wasn't long enough. Okay? And so, but you do it at the expense of essentially, in this case, the water's moving faster, but you have less of a flow of water here. Okay? I mean, the total amount of water is the same, but you don't have that bigger area of the water that can drench the plants, and so you need to keep that in mind. All right, and so I wanted to look at another application now, and this is basically just a blood pressure problem. We'll use Bernoulli's equation for this one too. Now, 120 over 80 has often in the past been considered to be a healthy blood pressure. Not so much anymore. Now we say that maybe it's better to have it be, say, 115 over 60, or even 110 over 60. And particularly that lower number is supposed to be a smaller value, because that's your resting or diastolic blood pressure. And so this is your maximum blood pressure in units of millimeters of mercury. So in other words, 120 millimeters of mercury is what we call our gauge pressure. And this is your minimum blood pressure during a stroke of your heart. So your heart beats and goes through a maximum and a minimum pressure. And so this is kind of your resting. Your arteries get to rest a little bit in between heartbeats. And so if this number is too high, then that means they don't get a chance to rest. They're always being pushed on too hard. And that can cause capillaries to burst, and particularly smaller blood vessels in important organs like the kidney can be threatened by having a diastolic pressure that's too low. So this is your minimum blood pressure in millimeters of mercury. It's also what we call a gauge pressure. So let me just define gauge pressure. We have absolute pressure equals P gauge plus P atmosphere. Okay, and so why do we set it up this way so that P gauge isn't the same as P absolute? And the answer is, let's say that you're trying to measure the pressure in your tire and measure 0 because your tire is flat. Well, you know it's not really 0. There's still atmospheric pressure in there. So the gauge is measuring what's above atmospheric. That's what's important, because outside of the tire it's atmospheric. Inside it's atmospheric plus P gauge, and so it's really just measuring the pressure difference when you measure the pressure of the tire gauge. And so P gauge then typically tends to be then 1 atmosphere less than P absolute. And so here then we're talking about a gauge pressure of 120. Remember that 760 millimeters of mercury equals 1 atmosphere. That's the height of a mercury barometer when it's measuring exactly 1 atmosphere's pressure. And so 127/60ths is the gauge pressure in atmospheres. This is the fraction of P atmosphere. Or in pascals, 120 millimeters of mercury times 10 to the 5 is going to be your absolute pressure then. What is measuring is 120 here as a gauge pressure. It's going to be 120 over 760 times 1 atmosphere, which is 10 to the 5. So that's 1.57 times 10 to the 4 pascals. Okay, so that's your gauge pressure when you're measuring the maximum blood pressure. And then in this case, 80 over 760 times 10 to the 5 would be, in pascals, your minimum blood pressure, but just measured in a different set of units. So that gives us 1.05 times 10 to the 4. Pascals. Okay, so with these ideas in mind then, let's say that you are having your blood pressure measured with a sphygmomanometer. That's your blood pressure machine. But while this is happening, the nurse is also kind of multitasking. So you can't bear to look here. Your eyes are closed, looking away as your blood pressure is being taken. You've got white-collar anxiety for blood pressure. And but she's doing a surgical procedure with her other hand, multitasking, and then she reaches over to check your blood pressure, sees that it's 120 over 80, then tries to take this thing off, and tragically she severs a major artery in your arm, and blood starts to flow out. And let's assume the blood goes straight up. And it's 120 over 80. Let's find the maximum height that the blood will go into the air. So this is like a spatter analysis. If you've ever seen Dexter, he's he's got his own issues, but he's a blood spatter analyst. And he's an expert at looking at how blood spatters on walls can be used to determine the way in which a murder was occurred. Okay? And so here, let's say that the blood flow goes straight up. We have this height for the blood, and we want to figure out what that H max is equal to. So we can think of this blood flow as being a continuous fluid, where this is let's say this is 0.2 in the medium, this is 0.1 in the medium. Okay, and so down here at 0.1, we've got P1. That's going to equal, here, that's going to be P atmosphere plus P gauge. So that's going to be the total pressure that's measured in the arm at the point at which the blood starts to flow. So that's going to be P atmosphere plus P gauge. Then there's also going to be a 1/2 rho V squared term, because the blood is moving at a certain velocity through the arteries before it comes out. But we'll neglect that. We'll say that V1 is small, so that V1 squared is really small. Okay, so we're going to neglect that. And then here, because we'll call this point here y1 equals 0, we can neglect that term too. So this is rho g y1. That's also 0. And then here at point 2, we're going to have P atmosphere as the internal pressure of the air per unit volume at the top of this fluid column. The blood won't be moving at this point, so the velocity of fluid flow of the blood will be 0. And the height then will be rho g y1. Okay, so we can see here then that the P atmospheres cancel on both sides of the equation. This gives us P gauge equals rho g y1. Okay, so we can use this to solve for y1, which is our h value here. Call this point 1, 2, I guess is what I was doing. No, this is 2. Sorry. This is still 1. That's 2 up there, and then this is y2. That was the only place where I had the... This is y1 equals 0. Okay, so that's all good. So P gauge equals rho gy. It's kind of like a barometer in a way. And so y1 is equal to P gauge divided by rho g. What's P gauge? Well, at the maximum height, that's going to be the systolic blood pressure, which we calculated over here. This is the 120 millimeters of gauge pressure divided by 760 times 1 atmosphere. So that'll go in here. That's 1.57 times 10 to the 4. So you wouldn't just want to put in a 120 there. That would be in completely the wrong units. Absolutely incorrect. Then we'll use the fact that the density of blood is probably about the same as the density of water. I say that the density of blood is about the same as seawater, which is interesting because evolution theories indicate we came from the sea. And so, but that's about 10 to the 3 kilograms per meter cubed times g, 10 meters per second squared. So that gives us 10 to the 4. That cancels out the 10 to the 4 in the numerator, gives us 1.57 meters. Okay, so 1.5 meters, that's like 5 feet. Okay, so if you're standing here 5 feet and you're more than 3 feet, your arm is more than 3 feet from the ground, you'll hit the ceiling. Okay, and so that means that your heart is a great pump because your heart is able to put out enough pressure to basically cause the blood flow to go all the way to the ceiling. And so it can go all over. If you're off at some angle, it can splatter in any particular direction. But will it continue with this flow rate forever? No. It'll go up and down like this as you go from 120 over 80, although your blood pressure may go up once you realize that your artery's been severed. But after about 20 seconds or so, you're going to start to bleed out. Okay? And so they consider this kind of a threat to your health, where you have rapid bleeding, to be the most serious. And so if you had 3 people that are laying out on the ground, one has got this kind of profuse bleeding, one of them's been poisoned, and another one has gone into cardiac arrest, you treat this one first, because this person can bleed out in less than a half a minute because the heart is such a good pump. Now, how do you treat them? Well, the first thing you do is you come in there and you push down with a gauge pressure that's equal to 1.57 times 10 to the 4 pascals. You've got to be able to push with that amount of pressure to stop the flow of blood out of the arm. And so that's what you do then, is you get down on that thing and push down as hard as you can with direct pressure, and then wrap something around it that will really hold it tight once you've been able to control the bleeding. Then once you've done that, then you would go to the person that had cardiac arrest. You'd apply CPR and do whatever you needed to do, but that person probably has about 5 minutes before permanent damage would be done from cardiac arrest. And then the poisoning, depending on the kind of poison, it could be half an hour, you could get them to a poison control station, give them an antidote. And so that would be in level of importance in terms of the severity of the life-threatening situation. That would be the third option that you'd go to, is to treat that person last.